All right, the second law of thermodynamics and entropy. So when we're looking at the first law, we can't really explain everything. And I mean, I'm a big proponent of the first law, and it really does explain a whole lot. And we were able to use it for a lot of different applications. But what it doesn't explain is sort of directionality. So we could see we have here a mechanical equilibrium or a thermal equilibrium. What we're seeing about an equilibrium is that it sort of like reaches something that's very stable. So in the case of a thermal equilibrium, because they're all pretty intuitive. If I have something that's really hot and something that's really cold and they're touching, eventually they will equate in temperature and stop transferring heat. The first law doesn't really tell us why that is. Doesn't really explain that. And I have another thermal equilibrium type of thing here. I have ice cubes in water at 0 degrees Celsius. They won't seem to melt macroscopically, and the ice won't, so the water won't seem to freeze. But why is that? Why is it that it's a stable point? If I'm looking at the seesaw here with the two kids sitting on it, if they're just sitting there and let's say they have the same mass, it won't move. Why is that? So these things are very easy to intuit. And if someone were to ask you, if you put 3 kids on one side of that seesaw, you would know exactly what would happen. But can you quantify that? Can you understand how that works? And another type of equilibrium I have here would be chemical equilibrium. So in a battery, you basically are transferring electrons based on an electrochemical reaction. And when the electrochemical reaction is sort of done and there's no chemical pressure, if you will, to move it over, the battery's dead because the reaction won't continue. So we need something to explain equilibrium. We also need something to explain how energy disperses itself. What we will see is that the second law comes in for the rescue here. And it's something that we really haven't discussed in other classes, these non-idealities. You usually assume everything's ideal, nothing, no frictional effects, no air resistance, nothing like that. The second law kind of takes care of that. It's kind of like a catch-all for all of those things. And it will explain the heat death of the universe and also explain why time goes forward. So it's a very, very powerful law that has a lot of ramifications in a whole lot of different fields. So let's kind of see how that goes. So from physics and chemistry, you basically taught a whole lot of different processes, and they kind of lied to you because they told you there's nothing to dissipate the energy. So the most common example I could think of is the ball on a hill type thing that you can do in physics. And you say that at point A at the top right, the point A, the ball has maximum potential energy, and at point D it has minimum potential energy, and at point G again it has maximum potential. And on the flip side, kinetic energy is 0 at A and at G, but it's really high at D, which is kind of what makes it move. And in physics, they kind of tell you this goes on forever. They also show you the pendulum. So if I release the pendulum from point 1, it will forever go from 1 to 5, back to 1, back to 1, 5, back to 1, et cetera, et cetera. Which in an ideal world, in an isolated kind of system with no dissipation of energy, that's true. It will go on forever. If that was the case, if they didn't lie to you, then you could say that, like, let's say I have this piston device up top of the blue thing here. If I expand the gas in there, and the piston then pushes on this spring on the right, it will compress the spring, which will basically hold on to all that energy that just got expanded. And therefore I can release that spring and it will push back on the piston and compress the gas again, and it will go on forever. If that's the case for any of those 3 processes, then we've achieved perpetual motion, and we know that perpetual motion is impossible. So the reason that they kind of lied to you is they didn't really want to lie. It wasn't a nefarious thing. They were trying to make the math easy so you understand these processes. And then afterwards, when you do things like the second law, you can take into account all these what we call dispersive effects. Okay, so there are two things at play here, as you know. You have friction that will kind of ruin the process, that will ruin the, not ruin, remove some of the energy that say this piston as it expands, it will release some of its energy in the form of heat into the walls of this container. And that's one example as to why this won't forever go. You also have resistance in the spring in the form of K, and that will also remove some of the heat. Other types of dispersive effects include mixing or air resistance, as you've seen. I have electrical resistance, so that's why I can't have a wire forever have a current. The wire itself has a built-in resistance that will take in some of the heat. Inelastic processes, chemical reactions, all of these things absorb some of the heat and have some sort of an efficiency built into them. The other thing, which is somewhat related, is that we can't say that every point in every process is always at equilibrium. And equilibrium, again, meaning that there is no driving force. If I say in the rolling ball example that at A and at B and at C and at D I have equilibrium, well then why is it moving? Why is it even going at all? So I can't really impose this equilibrium at every single point, at every single process. In the case where I ignore both of those things, we call this a reversible process. And so all the things that we've done in previous courses and in the first law assumed total reversibility. Okay. And so a reversible process defines what equilibrium actually means. Okay, and I have two types. I can have internal reversibility or I can have external reversibility, and I can have both. So in internal reversibility, that means that the system doesn't have any dispersive effects. Okay, so there's no heat loss within the system. And external reversibility imposes the same thing on the surroundings, and a total reversible process that has both built in. Okay, for any of those, we're assuming that work and heat are state functions. Okay, and so if you remember, we use that the delta, the lowercase delta to denote the change in Q and the change in W, and that was because they are not state functions. Meaning what? Meaning that if I start at point 1 and I go to point 2 and I go back to point 1, I will have lost heat, I will have lost work or produced work or whatever. Whereas if I take any state function like enthalpy or energy or anything like that, if I look at point 1 and I go to point 2 and I come back to point 1, then it should be exactly the same. The path that I took does not matter to the value of a state function. So for reversibility, we're assuming that Q and W will go back to their original value, which is why I am allowed to say that at A, I have a value for the kinetic energy, and as the ball goes back to G, it will have the same value of kinetic energy and potential energy. I'm not losing anything because I'm saying it's reversible. So we're assuming that these things are reversible, which is, state functions, which obviously is not the case. How do we visualize a reversible process? You could think of a gas trapped inside this cylinder, and the gas will have a pressure going up, okay? And you put a bunch of weights on it to weight it down, so it won't move, okay? Now, if you took the weight off, right, if this was one massive weight, it will expand. And we've done that for the first law, we're talking about expansion. And as it expands, for a non-reversible process, for an irreversible process, the friction between the red top and the blue walls will make the, will have some heat effect that will make the process lose energy through heat. Okay, what we will do instead of having a big mass that you remove, imagine it's a bunch of tiny little masses with each mass being equal to dm. And basically I can integrate all the dm's and get the big mass m. Okay, so I didn't make the masses even small enough. Imagine they're tiny, 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 like the size of a molecule or something. And then I remove the mass one by one. Okay, and as I remove the masses one by one, the red cover for the gas will increase because there's a pressure from the gas. Because the mass is so small, I will never attain the threshold for friction, and I will not lose any heat to friction. So the red and the blue will not lose friction. And in that case, heat is not lost. And so all of my energy is conserved. And so when I pull all the masses to the top, away completely, the gas will reach a mechanical equilibrium where the pressure at the top and the pressure bottom are equal. And I didn't lose any of my energy due to this expansion due to friction. And then if I put back those yellow bars one by one, again, I will not lose any heat to friction between the red and the blue, and I can re-attain the original spot, as you can see in this particular picture. That would be one visualization of a reversible process. So what does it mean for a reversible process? That means that at every step, whenever I remove the dm, I'm at equilibrium, right? So if I remove one yellow bar off of that, it will move up for a second and then it will stop. And then it will seem to have no change. There will be no change. So every tiny dm step is at equilibrium, okay? And that's obviously not attainable. We cannot actually get this reversibility, but that's how we visualize a lot of processes to be able to quantify them and use equations as we will. Okay. So let's talk about what entropy actually means, because entropy is going to be the thing that quantifies this reversibility and this ability to explain why processes have these dispersive effects. Okay. So before I get to entropy, I want to show you a parallel with mass and energy, and then I'll do entropy. So I could have done at the beginning of class is I could have just at the beginning of the first lecture, say, what is mass? Well, mass is some property that's intrinsic to the system, that's extensive, and it has to be conserved in a closed system. And that alone defines mass. Because if a kid asks you what mass was, how you explain to them, I ask you get all philosophical, but from a mathematical point of view, this is the definition of mass. Looking at energy, I can, again, someone asks you, what is energy? I mean, really think about that. What is energy? So it's just this term we kind of came up with to account for something. So in this particular case for energy, we say energy is an extensive property. And if you have an isolated system, its energy will have to be conserved. Okay, what do we call this E? And the only way for me to get energy in and out of a system is through heat or work if the system is closed. If it's open, then all hell breaks loose and we have to account for the first law of the system. But for a closed system, the only way to get energy in and out of a system is through work or heat. So that kind of defines energy for us, and we can kind of play around with that. And then this defines the first law of thermodynamics. So again, both mass and energy, even though they seem very intuitive to you, it's really hard to define, pinpoint what they are. And this sort of approach gives you a mathematical definition for them. Well, let's do the same thing for entropy. So we'll say that entropy is an extensive and intrinsic property, and we'll call it S, okay? And we will say that entropy can only be transported via heat transfer. The only way for me to get heat entropy in and out of a system is through heat transfer, okay, for a closed system, okay? And we can also say that entropy is only produced. I cannot ever destroy entropy. I can produce it or I cannot produce it, depending on the process. If the process is truly reversible, then I am not increasing the entropy. I am not producing any entropy. If the process is irreversible, which is the vast majority of processes, then I am producing entropy. So I'm forever increasing the entropy. I'm always adding more and more and more entropy. Okay, so let's look at it from a mathematical definition. For a closed system, because what we're going to follow the same way we did it for the first law. For the first law, we did first law closed systems, then we did first law open systems. We should do the same thing here. So it's easier to understand second law incrementally. So for a closed system, the change in entropy in a system, so how it accumulates within a system, will equal two terms. One, the first term with a big sigma, is the rate of entropy transport in or out of the system through the system boundaries. Okay, and again, heat is not a state function, so I got to put that delta thing there. And so it's delta Q over T. Why am I putting that big sigma? Because I can have different parts of the surface have entropy coming in or out. So I'll just add up wherever entropy comes in or out. We will look at that area and see what the heat transfer of that area would be, and I add them all up. We'll see that in a few examples. Then I have this sigma dot term on the right side, and that stands for entropy generation. Okay, and so that thing, the sigma dot thing, is equal to 0 when the system is reversible. So when the process is reversible, I'm sorry. This will go to 0 when the process is reversible. This will likely stay unless it's adiabatic, and then I can discuss the change in entropy. So S, entropy, is a state function. So if I start at one point and I come back to it, the delta S should be 0. And if I have something internally reversible, so again, I'm getting rid of that sigma, and I'm getting that ds is equal to dq over t. And again, I can sum them up over a bunch of different areas. I'm just showing you one heat transfer, but I can have multiple. Okay, so let's talk about some consequences, important consequences. So if I have an irreversible process, which again is most processes, then this sigma dot term is got to be there. And by definition, I can only generate entropy. I cannot destroy entropy. So this has to be a positive value. If it's adiabatic, then all these Q's go to 0. I have no heat transfer. If I have no heat transfer in the system and it's irreversible, then I could see that ds dt has to be equal to this sigma dot. And since we define sigma dot as the rate of entropy production, and since entropy production has to be positive for an irreversible process, this means that I will forever increase entropy. So the entropy of the universe forever increases. That's one consequence. Okay. The other thing is to discuss equilibrium. What is equilibrium? Well, equilibrium will happen when I have no change in entropy. If I have a change in entropy, then it will go in the direction until it maximizes entropy, and entropy will be 0. ds will be 0 at that point. Okay. So any system that's trying to do something will have a directionality to it because of entropy. So if I have a hot object in touch with a cold object, the temperature will move from the hot to the cold until both of them have the same temperature, at which point ds is 0. There will be no more change in entropy. That we will call thermal equilibrium. Okay. At the very beginning, when one is 100 and the other one is 0, ds will be greater than 0 for that particular process, and we will call that a spontaneous change, and we will have a directionality of something, whatever we're trying to quantify, to get to an equilibrium position. So it could be temperature, it could be pressure, it could be chemical potential, whatever it is, that will try to drive the reaction, the process to a ds going to 0. If ds is less than 0, if you calculate something for ds is being less than 0, so for example, I'm trying to transfer heat from an object that's 50 degrees Celsius to an object that's 100 degrees Celsius, that's unnatural. And so if I could do it, but I have to put work into that. I have to put something into it in order for that to happen. And we do that all the time. We're trying to go against the grain of entropy because we're trying to get something out of a system. We do that with our body. From strictly speaking, all things are fighting this entropic force to stay alive. So we put food into our body, we put water into our body to basically drive this unnatural process, because we are not at equilibrium. If we were at equilibrium, we would be dead. Which again talks about, so like, let's say you have a dead body or something like that, and you're trying to reanimate it. That will be kind of difficult because all the processes in the dead body have reached a state where the entropy is 0. So you have a moment of grace period, and you can resuscitate people. But when you reach a certain point, chemical reactions in the body, mechanical reactions in the body have reached a state where ds is 0, and it's kind of hard to bring them back from that brink. So that again goes to the discussion of steady state versus equilibrium. Being alive is steady state because nothing, I mean, things change, but by and large, if you think of yourself throughout the day, things don't change with time. But if a person is dead, they're dead. That's at equilibrium. There will be no changes. There will be no driving force to get from one point to another. So that's the difference between steady state. Steady state will require input for it to stay at steady state, whereas in equilibrium, it just is. ds is 0, and you don't have to do anything about that. So if you have a state where a building doesn't collapse, it's because you designed it so that the structural forces and the delta forces go to 0, and that takes care of your equilibrium, and you're in an equilibrium position. If you don't, then you have to constantly feed energy into it so that it doesn't collapse. And in that case, we would say that the building is not at steady state, not equilibrium, it would be a steady state. So if you do have a point, if you have an old building and you're trying to make sure it doesn't collapse, you have to input energy into that building, whatever way you have, to make sure the delta forces are 0. So that kind of brings back that idea and gives you a quantification for that. The other thing to talk about is cyclical processes, and this is known as the Clausius inequality. So for a cyclical process, because S is a state function, if I start at a point and end at the same point, ds has to be 0. So the cyclical integral for ds would be 0 for a process. And so that would mean that the second law would not have the ds dt thing on the right, and it would just be equal to 0 for a cycle. And that would mean that the big sigma with the heat transfer and the sigma dot would have to balance out to create 0. And since I know that the entropy production has to be greater than or equal to 0, that would mean that the heat transfer has to be less than or equal to 0. Let's go over some examples.